Good morning, making sure everybody can hear me okay. Welcome, thank you for coming to our talk. Next two slides, of course, I don't really need to cover as much. Go with that one, there we go. John covered all this, right? So I don't really need to harp on this, but my main thing here is I'm very proud cyber dad, as John said, because I get to introduce my daughter, Isabella. So Isabella, anything else you wanted to say?
Hi everyone, my name is Isabella Barnett, also known as Angel Hacker. Like John said, I'm a cybersecurity engineering student and I'm super pleased to be here.
All right, so before we dive in, when we were discussing this, we said, okay, how do we do an intro to the problem that we're talking about here? So we want to come up with real world analogies. So we're assuming most people have probably played the telephone game, right? Either when you're a kid or at a party. If you haven't ever played it, this is the basic concept, right? Somebody comes up with some phrase, they whisper it into somebody's ear, it slowly goes down the line, whisper to whisper. And over the course of that, either because of omissions, additions, or people wanting to be funny, it changes along the way until the end. And then the person at the end says, oh, here's what I heard. And it's usually something completely different, right? So take that party game concept and then apply it here to the web. So it's the web telephone game that we're essentially dealing with. Now, this is a very rudimentary architecture, right? There's way more complex stuff happening here. But the idea is that same telephone game of you have an end client sending a web request. There's multiple different intermediaries or different systems where that data is going to flow through. So in this case, CDN, that's what I do, and then protecting customer apps. So here, if we go, with this next flow here, it's the proliferation of bug bounty hunting. That's really changed from my perspective, what we look at, what we do, different issues that we find. So in this scenario, right, you have a bug hunter, they're sending stuff through, and this is where we were kind of correlating, or I was putting into different buckets problems that I was seeing. Say, hey, we're supposed to block attacks, something missed, what is this? And I started putting them in these buckets and realizing, okay, there's certain commonalities here. But here again, if we're looking at the flow, you have the different layers where you're doing security detection logic, maybe upstream in a CDN. Inside the application, I'm sure there's a bunch of security checks. And then the data is used in some way. So going through these security checks, well, then when data is being sent, the problem is after those security checks, there's something inside these applications that's actually processing and changing and manipulating data. And it turns it from something that at that point was not an attack or malicious into something that actually works. Okay. So this is a big takeaway. If there's like one thing you take away from this talk, it's CWE 180. When I was putting it into these buckets and thinking, okay, what's the commonality? It's this order of processing problem. Just like you see here on the screen, a security check, later on data changes, recipe for disaster. So this is a rough outline of what we're going to talk about for like the next 30 minutes. How Isabella and I were working together, obviously I got a lot of data where I work, but then I would group it into these buckets. I would sanitize all this stuff, right? So I could talk with my daughter about it. And we made these into like research projects. And so that's really where Izzy was helping out to do all this analysis.
So we have a QR code here that will take you to these dojo labs created. Yes, We Hack has this platform where you can create these labs to simulate different process flows. So we've created individual labs for the different topics we're going to be talking about. And since we don't have time to go over them, you can follow this QR code and hack it yourselves. So first up, we're going to go over Unicode just a little bit. It's a broad topic, but first up is internationalization. It's this process of making sure that code can handle languages from around the world. So many different character sets and glyphs that need to be handled by these computers so that they can understand each other and maintain data integrity, including things like emojis. So this is a great tool, a UTF-8 visualizer by Sonar Source. You can see here in white the Unicode code point. This is the numeric representation of the glyph. Then you have the raw bytes. This is the binary that would be stored in a database or in memory. And then lastly, you have the UTF-8 encoding there at the bottom. This is how it's going to be sent over the web in web requests. Unicode is such a large topic that we don't have time today to cover everything, but we wanted to focus on kind of three main key things that are critical to our talk today. Unicode represents a wide range of characters and can be multi-byte in length. However, ASCII, on the other hand, is a subset, which is only a single byte represented in 7 bits. This means it requires less storage space compared to Unicode, which can be longer and sometimes require more storage space. So the real issues we get into here is how do you maintain this data integrity when you're switching between Unicode and ASCII? So first up, we have decoding errors, specifically multi-byte awareness. That leads us to CWE 172, which is encoding errors. This also includes decoding errors or any sort of issues that you get when you're decoding and you sometimes get incorrect output if text is garbled or not what it originally was. Again, with the visualizer, you have the capital letter A, an ASCII character, and then a laptop emoji, for example, which is multi-byte. As you can see here, the leading bits will signal the character byte length. If it is a 0, that means it is a single byte character. And on the other hand, you have 4 leading ones. This means it's 4 bytes long. As you can see, there's these different continuation bytes with a 1 and a 0 at the beginning. This signals that these bytes are linked. It is a part of a single character. It's working together to represent it, and they can't be separated. But what if during processing, it is treated as separate bytes? If these leading ones are switched to 0s, you get something called mojibake output, which is Japanese, roughly translates to character mutation. So if you change those leading ones to 0s, it separates the characters in 4 different separate characters that have no relation to the original intended input. I'm sure most of you know what Burp Suite is. It's a great tool to test web applications. So let's say we're wanting to input this left angle bracket. It's multi-byte, so you're going to take the UTF-8 encoding at the bottom, going to input it into Burp's decoder, and as you can see, Burp's decoder is not multi-byte aware. You get mojibake output 3 random Unicode characters that have no relation to the left angle bracket. But what we can do is go to the Burp store and install Decoder Improved. It has Unicode support. It can correctly display these characters because of the Java swing elements. As you can see, when using Decoder Improved, which is multi-byte aware, you get the correct decoding and you can see the left angle bracket. You can also go to the Burp store and get Activescan++. We have made some updates that have been released as of today, specifically the suspicious input transformation. You've got a left anchor and a right anchor. These are used for taint tracking so that whatever your input is, you'll be able to find it reflected back in the output and see if there's been any transformations. Specifically, we want to see if the Greek capital letter alpha has been transformed into 2 characters, Latin capital letter N and device control 1. This is going to be an indicator that whatever decoding is not multi-byte aware. This could be a potential exploit vector that you could pursue.
Okay, so next subsection here under decoding errors. And just highlighting again, this is not typical like Unicode stuff that we're talking about, but it's important because this is a pipeline processing. You got to get this stuff right before you do any of your security logic. So just making sure we're level setting there. So here it's overlong encoding. In this case, we're referencing KPEC 80 because it talks specifically about this scenario, different UTF-8 encodings. So I love real-world analogies. As we were discussing what this is, it's like, has anybody else ever received an Amazon package? You open it up, there's a bunch of filler in there, packing material, and you open and pull out another Amazon package. You're like, why didn't you just send me this package? So needless packaging. That's essentially what this is. So back to the visualizer here. You have the normal, capital letter A that we've kind of been talking about, single byte, right? And that leading bit is 0. It's only 1 byte long. However, you can take that data and forcefully split it into 2 and do overlong encoding, in this case, 2 bytes. You can do 3 bytes, you can do more, but we're keeping it basic here. The scenario is, as Isabella was saying earlier, those bits mean something in those bytes. Some hold data. The beginning ones are referencing, is this a leading byte? Is it a continuation byte? So if we're going to force it into be 2 bytes long, looking, as you can see on the screen there, you have to take a piece of data and move it. Because 1 byte saying, oh, we need a 1, 0, this is a continuation byte, the rest of the data is in the other byte, right? Now, the key here is you're sending that data across. It's still supposed to represent the exact same character. What you don't know is how's the application going to respond. Now, early UTF-8 encoding, this was allowed. They changed it to say, no, no, you shouldn't do this. It's really not good reasons to do this. It can cause problems, as we will show you. But is an app going to block it, not let it through? Most don't like to do that. Are they going to correctly normalize it back to the ASCII character? Or is it going to be a mojibake situation? So going forward here, we'll take a look. This was something fun for us as well as we were researching. If you look at those characters at the top, I see some heads nodding. You have a dot, a forward slash, and a backslash. Then you look at the bottom and you see if it's UTF-8 encoded. Was there anybody doing web security in 2001 and recognizes what this might be in relation to? Anybody? Can't see with the lights. Okay, this was also referenced in Miko's keynote yesterday when he was talking about Slammer and all these different things, but we'll show you what it is here, NIMDA. So I was working actually at the time protecting some government websites, right? Oh, hey, he's in here, there we go. That's funny, threw me off. Protecting the websites, I saw this coming in, I'm like, what the heck is going on here? Fortunately, ours weren't running this, right? So it didn't impact our environment, but I had to figure out what was going on. So this was using that overlong UTF-8 encoding. So it had a problem where there were some security checks looking for dot dot slashes, directory traversals. It bypassed that, then it gets normalized back, right? And so then it was a problem. Okay. So another example from a tooling perspective, like, okay, that's interesting, but how else can this be used today? So for SQL injections, SQL map is one of the very popular tools to do this. In this case, there's tamper scripts, all sorts of different ways you can take whatever you wanted to send, obfuscate it in some way, and see if it bypasses some security logic. And in this case, what it's doing, it's taking the ASCII space character, overlong encoding it to 2 bytes, sending it on its way. So here, we want to show one example of, quote unquote, security logic and where this is causing the problem. So here we're using that regex 101 website, and we're able to take that exact same payload we saw, pass it in the query string, you see up there in the URL bar, and then you apply some sort of regular expression against it. Now this is very basic, but let's say you're looking for select and from, and in between there, you can have some space characters and then something that's not a space. The problem is this does not match, right? It shows you up in the corner, this regex doesn't match, and the question is why? And then you look at the bottom and you see the test string. Now in this case, this website was not normalizing the overlong encoding back and putting in a space. Kind of a mojibake situation says, here's 2 bytes. We can't really represent this, so it's putting in a replacement character. But the point here is this pipeline. You're supposed to do URL decoding, then you apply your security check. Because the decoding was wrong, your check fails. So again, take this as just one small example that you can check back at work.
And next up, we have byte truncation. And our case study for today is going to be a bug hunter who found control line feed injection in Microsoft. So here you've got the payload and you've got these 2 characters, carriage return and line feed UTF-8 encoded. But if you submit this as expected, you get blocked, access denied. They understand what you're trying to do. But as you can see here, the attacker has the 2 UTF-8 characters encoded, sent in, and in the response, you can see that the set cookie header has successfully been injected. How did they accomplish this? With the tool CyberChef, we're going to do a URL decode recipe, and as you can see, you get these 2 Chinese characters. This is not control line feed. How is this executing? What's happening? This is a potential scenario. As in most of these examples, it's a black box. We don't know what exactly the web application might be doing or what processing might be happening, but this is potentially what could be going on. A byte ordering, if they're doing little endian, they're going to take the least significant byte, the one on the right, and they're going to store it first. So with that in mind, with the Chinese character, you've got a single byte buffer and then 3 bytes. The least significant byte is going to be stored first. It fills that buffer and the rest of the bytes are discarded. So you just have this least significant byte, which happens to be the carriage return. This is called byte truncation. Again, with CyberChef, if we apply the encode text recipe, specifically US ASCII 7-bit, this is going to mimic what might be happening server side, where it's just storing a single byte You're going to get byte truncation, and you get control line feed characters right before the set cookie. Here's a great tool called Shazzer by Gareth Hayes. You can input a hex character, and then you get back different Unicode characters that would be truncated to that character. It's great for testing. Again, Activescan++, the PR request. Between the left and right anchors, you have the Hangul symbol. If you input that and you get back a left curly bracket, this could be an indicator that you could do server-side template injection.
All right, next up is Confusables. Generally speaking, when I was starting to talk with other people about, oh, what's your talk about? And I say, oh, Unicode, they immediately think of this. Confusables, especially when you think about domain spoofing and phishing and that kind of stuff. So we're not really talking about that. We're talking about more of these specific web application layer stuff. So jumping in here. Going back to our map scenario, if you, in this case, have somebody, let's say they're in Greece, they're sending some data, Greek characters, right? Greek capital letter alpha. They send it to a website that's only receiving ASCII. Generalized question, what do you do? Right? Are you going to block it? They don't want to do that. So I say, well, I don't have that character. I have something that kind of looks like that character. So I'm just going to switch that to this other character, right? A normal ASCII capital letter A. That's not going to cause any problems, right? Right? So it's the raised eyebrow here. Of course it's going to cause problems. Otherwise, we wouldn't be covering this section. Normalization forms, right, from the title. Again, there's 4 major normalization forms. They do different things. They're used for different purposes. We're mainly focusing on the bottom 2, capability, because that's more of a confusable, look-alike, best fit mapping, which we'll talk about here. It is important at the top, though, to realize when you're doing decomposition and composition. Isabella's going to talk about that a little bit later. But highlighting here the 3rd row specifically, we were showing the one with the circle around it. There's a couple different names for it. I call it enclosed alphanumerics. I see these a lot in SSRF type of attacks. Anything that's wanting you to look at the domain name and try and figure out ways around security filters. On the Unicode website, they do have a lot of really good tools. If you've never checked out the website, please go check these out. This is where it's showing you different IDNA processing for those domain names. Here in the field, you can see it's kind of highlighted. I was putting in an example of enclosed alphanumerics for the loopback IP, 127.0.0.1. Think back to the regex that we were just doing. If you look for 127.0.0.1, right, digits and dots, this is not going to match. Right? But in the bottom, you can see the different types of IDNA processing that may be there. They do get normalized, right, into actual ASCII and integer values. So for the next example, we wanted to kind of mimic what could be happening. So especially in an SSRF situation, you get data from a query string, some sort of parameter. It's probably going to be called in a sub request with some sort of web client, right? libcurl, something like that. Makes a sub request, does whatever it's supposed to do. So we're just mimicking this behavior here again. You just get at the command prompt using curl. This is mimicking that SSRF scenario. And as you can see down on around the 4th line, it does get normalized back to normal ASCII text, and it resolved correctly to the loopback IP. All right, so case study time. It was great, again, as we were researching, saying, how are we actually going to explain this stuff? Because I can't use my stuff from work. I have to sanitize. So anytime I was seeing stuff that was like, oh, that's the same topic, it's public information, perfect. So this was done by Searchlight Cyber in July, and it was talking about Unicode normalization issues in .NET Nuke. So we're going to take a quick dive here. This is the web request they were using in the example. The only takeaway you really have to have here is down in the bottom. This is a post request doing multi-part with a file attachment. The key here is the name of the file. And specifically the name of the file, they were doing some UTF-8 encoding of Unicode characters. So keep that in mind. This is where it came from an attack perspective. But now we're going to look at the code, the payload, and see exactly if you do a UTF-8 decode, what does this look like? And again, we're thinking confusables here, right? So in your eyes, you're thinking, oh yeah, those are backslashes and dots. No, they're not. These are different Unicode characters that look similar, but a lot of these are the full width versions of their ASCII counterparts. So those aren't actually backslashes and dots. Keep that in mind. Okay, so now we'll look at the code. There's a lot of different things in the blog post. I suggest you read it fully because it's fantastic. We just pulled out a few pieces that were directly related. So here we're talking about a regular expression. It's checking the file name. So remember what we just showed on that screen. This regex is looking for ASCII dot characters because it says, wait a second, we want to make sure that dot that's in relation to the extension of the file is the only dot that's allowed. If there's any dots before that, we want to strip them out, get rid of those. Now the problem is at the bottom, as you see, the regex again, that's not going to match. Those aren't those ASCII characters, doesn't match. So then it moves on to the next section of code. Now you're back to CWE 180, right? This reoccurring theme. Apply a security check. Afterwards, let's do what's called best fit mapping in Microsoft. So highlighted at the bottom there, this is a code page 1251. So you may be asking, okay, what is that? So you can actually go on Unicode's website and find these different code pages. So again, this is similar to the normalization forms, but these are direct mappings that Microsoft has depending on the code pages you want to use. But we're highlighting there, and if the next screen will show you here specifically that mapping, just so you know, this relates back to our payload that we were talking about. So that full stop gets translated into the normal ASCII's dot character. So remember, that would have matched the regex, but now it's afterwards it gets changed. So at the bottom is the updated payload. So now if you look at the beginning, and you have those double backslashes, well then in a Windows environment, right, you have an absolute path, you're dealing with UNC and saying, oh, wait a second, this is a remote server, this is a remote host. I can make an outbound connection there, and if you look at what that domain name is, OASTify, right, you have Burp Collaborator, out-of-band beaconing types of domains. If this .NET nuke is vulnerable, it's going to make an outbound connection and it can leak credentials. And that's actually what they found when they did this write-up. Due to time, again, we can't dive into all the case studies, but I did want to reference this from Orange Tsai, fantastic researcher, Black Hat Europe talk. Go to the website, worst.fit. It's got great tooling. Highly suggest if you're interested in this, go check it out. Another utility, you can go here on the Unicode website. You can put in an ASCII character, hit return. It's going to show you all those different variants of Unicode characters, depending on the normalization form, may map back to that. All right, back to Activescan++ updates. So this is a check generalized to say, let's look to see if there's any normalization forms that are happening here. It's not specific to any one, you just want to see if there's something going on. So you have the same left and right anchor, the same type of processing. The key here is what character do you use efficiently to do a quick test? So what's interesting is the Kelvin sign. It's one of the few that actually under any transformation normalization form will get mapped back to a normal capital letter K in ASCII. So very, very useful to quickly test. So we were mentioning these Activescan updates, but maybe you're getting tired of looking at PRs. So we wanted to show this live in action. So we're able to run this tool, right, with the updates that we had. Activescan says, hey, we found a suspect transform problem here. So in this case, you're looking at the raw request, but on the right-hand side, you can see the data, right, that we're sending. So you have your left and right anchor. In between, you have the UTF-8 encoded Kelvin sign, and you hit go. If you then click over to the response tab, we also did render just for you all visually to quickly see what we're talking about. You get your left and right anchor, and in between, indeed, it is now a capital letter K. So you know there's some sort of normalization happening there, and that's the idea, right, with Activescan. It's saying, hey, here's something you need to look deeper into. Okay. All right, next one, casing. This is another one that was interesting. Actually, we'll go one more for it. When I was looking at this for work, I got an example, cross-site scripting issue. They said, hey, this didn't get blocked. What is this? What's going on here? So it was similar kinds of processing when I was looking, but it wasn't fitting into the existing buckets I was already researching. And so what is going on here? So taking that data at the bottom, right, you have the script tag. So what was happening here, this UTF-8 character, right? And it's got a long name, so I'm actually going to read it. Latin small letter dotless I. That's not an ASCII I, right? So if you end up doing some sort of regex and trying to apply that, if you say, hey, look for less than in a script tag, of course, that's not going to match. That's not what that character is. So again, we're back to this common theme. But the question is, why did it turn into a script, or the I? So now you get into these casing charts. right? So you have case folding, you have lowercase, uppercase, title case, there's all these different combinations. So it depends on exactly what language you're using in processing here. But think about this, especially any bug hunters out there, or if you're actually on the application security side. Any input that you're getting that you apply an uppercase transform to, you probably have reasons to do that you want to normalize stuff. You don't want these collisions with an admin with a capital A and an admin with a low, and you can't reconcile. But keep in mind, there could be a Unicode type of mapping that's associated here. So in this case, that dotless I was getting changed. So here we did a quick just to demo in Python, this kind of internal processing. So we take that same payload, we apply a decode to it, then you apply the upper method to it, and then we're going to show you both the outputs. So if we hit enter, this is the output you get at the top is what it would have been. It does not execute, right? The browser is not going to treat that as a script tag. The problem is that uppercase transform changed that character back into the capital letter I. Now, here, the mileage may actually vary, right? We did a little bit of research looking at this to figure out, does this work? Wait, will this execute? So it depends on the payload that the attacker might want to use and the context that it's in. The key takeaway, though, is it's changing those letters. And it's turning into something a browser would not execute into something that it might. So keep casing in mind and look in your application. Anytime you're using uppercase, lowercase, check that data. Okay. There was an update we did here to a different tool this time. This tool is called recollapse. It's another fantastic tool out there. It was doing similar types of things. I had heard of recollapse, and we were researching different tools to say, hey, what can we update and use for this? So I worked with the creator of that to add some casing tests as well. So this is another way you can do the tool. I think we have a screenshot. Yeah. So as an example, there's new flags. So you could put this flag on here and say, hey, here's the end result that I want. And it will give you different options to see from a casing perspective if you could use a different character that might map to it. So go check out recollapse. That was just updated, I think, today as well. Okay.
And finally, best for last, we have combining diacritics, also known as combining characters. So if you've got a normalization form that's performing decomposition, it will separate this character into two separate code points. And for our case study, we're going to be talking about a zero-click account takeover. So as you can see here, this would be a normal process flow for a password reset. A user would submit their email, the server would send it onto the database, which would perform a check saying, is this a valid user? If it is, it will send back a token allowing them to reset the password. So let's take a deep dive into the MySQL database. Let's see what kind of collation they might be doing. As you can see, it's 0900, that's the collation algorithm version, and then there's AI and CI, which means accent insensitive and case insensitive. But what exactly does that mean? That means if you're submitting this lowercase a with an accent and comparing it to the lowercase a and the uppercase a, for both of them you would get true. The database treats them as equivalent characters. On the flip side, you can see if it's accent sensitive and case sensitive, then of course they will not be true when compared. So now here the attacker is going to send in this email with a custom domain that includes a Unicode character. How is the database going to treat it? It's going to look at this domain and say, yes, Latin small letter a with double grav is equivalent and absolutely the same as the Latin small letter a. So when it receives this email and it's comparing inside the database, it says, yes, this is user@gmail.com. And here's the issue. When it sends back that token, it sends it to the user supplied Gmail, not what was stored in the database. Therefore, the attacker now has a reset token for somebody else's password. Here's a collation chart on the Unicode page, which demonstrates how the lowercase a can be collated and equivalent to all these other Unicode versions. And then for our final case study, XSSE has a really cool lab that we're going to take a look at. In the top URL bar, you can see there's the name parameter. We're just inputting a placeholder Unicode character, something with an accent. And you can see in the text area, it is properly rendered back. That can clue us in that some kind of normalization composition is happening here. and it might be vulnerable. If you take a look in the HTML source code down at the bottom here, you can see that it is a container element, which means that our input, our parameter input, is in between two text area tags. And as you can see, it is right next to that greater than symbol, positioned very conveniently so we can exploit it. On the backend server side, it's got free marker, and you can see that our input is being concatenated with that text area tag, and then all of it is together normalized. So our goal here is to how can we modify and change that greater than symbol. So we've got this Python script that's going to be cycling through different characters. They're being concatenated with the greater than symbol, and what you're trying to see is how this string would not start with the greater than symbol, meaning it would be modified. And that happens to be this character here, which is the combining long soldice overlay, a combining character. So when the greater than symbol is concatenated with this combining long soldice overlay, you get the not greater than symbol. This means that you're effectively changing that character entirely into a different code point. So you're going to take the combining long soldice, you're going to UTF-8 encode it and place it at the beginning of the name parameter. This is a fun little thing we noticed, not super critical to this, but it combines with the equal symbol in the URL bar, making it not equals, which is just a nice visual way to see that the browser is performing this composition. But when you submit the payload, you can see that it is modifying the greater than symbol into a not greater than. You have broken the context of that text area tag. You've injected an on-focus alert event handler and the alert pop-up, and boom, cross-site scripting performed.
Nice.
And then again, we've updated Activescan++ to look for this. This time, you're only having the right anchor because you don't want a left anchor. You want it to be able to combine with the greater than symbol before it, and you're trying to get the not greater than symbol. That would be a hint that there's some form of composition happening, and it's potentially exploitable.
All right, so to wrap up, I've got the sound bites. Got to make sure you have those takeaways. So it should be clear now, the very first one, that was that CWE 180. Again, that's the number one thing. If you're going back and checking your apps, you got to find everywhere that this may be a problem, right? Because we gave lots of examples of how it can be. Also mentioning validating that URL decoding. Again, that's not really Unicode normalization, but it's your entire pipeline, right? If you get it wrong at the beginning, it's going to impact everything else. And then also just normalization forms that are in use. Figuring out what you have, ensure that it's consistent with however you want to process that data. But obviously what we're showing here, it's most problematic if you're converting stuff into ASCII. And some of the kind of harder parts here is when applications do stuff kind of natively that you weren't thinking of. Like you maybe know, oh yeah, we're handling generally normalization in Unicode this way. But as we were showing, there's some built-in third-party libraries that may be doing something that you're not aware of. And that's the hard part. So again, that's why we were trying to update the tooling to help you go ferret out these different scenarios. Say, oh wait a second, something weird's going on here, let's go check it. So for both defenders, bug hunters, hopefully this information was useful. Go forth, find Unicode problems, and get those corrected. With that, we have a few minutes left, so I guess we can open up if there are any questions. We'll go from there. So thank you for coming. Appreciate it. And if there are no questions or you want to talk to us after the fact, we are going to go to that wrap-up room. So feel free. So thank you. Thanks again. Okay.